Great. So number of people have joined on. I appreciate that. Again, I'm Drew Sabo. I'm an electrical engineer with Westwood Professional Services. We're an engineering and a multidisciplinary engineering and surveying firm based in the Twin Cities in Minnesota, but with offices around the country, including Madison, Wisconsin. And through work at Westwood, I've been working on renewable energy and power engineering back about 20 years through utilities as well as renewable energy type engineering. I thought as Westwood is sponsoring the summit, I thought it would be interesting and worthwhile to try to do some sort of open, moderated discussion on electrical engineering topics that relate to distributed generation and, primarily with renewables. My intent was that this be sort of a wide-ranging and free discussion of a technical nature, but not necessarily going down the deepest technical rabbit holes. But I knew that would be somewhat dependent on who all decided to join in. And so in the interest of just having a kind of a free exchange, I'd encourage you through the course of this to introduce yourself, what background you're coming from, so we can kind of shape our discussion a little bit, and hopefully some things come out that are interesting, perhaps lessons learned from various people involved in the industry in distributed generation, perhaps different perspectives from different types of stakeholders, be they engineers, like engineering firms, utilities, owners, developers, all those types of aspects. And sort of informally, as a co-moderator here, I've invited Todd Montevideo, who is with MG&E and manager of engineering for distributed resources. I believe that's your current title, Todd.
Close enough.
Close enough. Okay. To help kind of as a participant and moderator in the discussion. And so, we'll see how this goes. We'll see, maybe there'll be some topics that come out of it that we might collectively in the industry here in Wisconsin have an idea for further exchange, further collaboration. I'd certainly welcome that, and hope the other participants will too. So with that, I guess I am interested in getting people to kind of introduce themselves, at least to, what kind of roles they're in, so we can get a sense of the audience, and then we can jump into the discussion. And I had created a list of topics of interest to me, and ones that come up frequently, all in an electrical engineering vein, and hoping that serves as some kind of basis for us to proceed and converse. But I really do welcome you and encourage you to participate fully, and hopefully we don't just talk over ourselves. I can help try to moderate that. If people are interested in weighing in, I'll try to make sure that people get a chance on the floor. So I'm going to stop sharing my screen for a second here, just getting a view. Now I can see all the people on the call. And maybe I'll just ask the various people who are registered here to kind of weigh in who they are, who they're with, what their background is, and then we can keep going. And then we can get the discussion going. So is it Stephen Ferns? If you're on mute, but if you want to stay on mute, you can. I could probably unmute you.
Okay, I think I just unmuted myself.
Yeah.
Yeah.
Hi. Welcome.
Hi, I'm a recently retired engineer, work mainly in the water and wastewater field. Lately, I've been dealing more with control systems and building energy management, and I'm trying to build up my technical exposure to distributed energy systems, PV. Long time ago, I used to do some hot water solar and passive solar, but PV is where we're at right now.
Great. Okay. Well, thank you and welcome. I know Lauren's with Renew, and thanks for being here, Lauren. I see move to Lee Gasper Galvin, if you care to suggest your reasons for being here and what you're interested in hearing about.
Can you hear me now?
Yeah.
Oh, okay. Yeah, I'd open up my, open my video.
Oh, hi.
I'm a PhD chemical engineer, and years ago I used to work for the Department of Energy in Morgantown, which was actually fossil fuels, but I always had my heart with renewables. So in more recent years, I've worked with electric vehicles and lithium-ion batteries. So that's my background.
Oh, great. Well, thanks for joining. Appreciate it. Katie Kramer. Oh, is that okay? Yeah. Katie.
Hi.
Hi.
Okay, the video's not working and there's not much to see, so you're all good.
That's fine.
I am a new solar professional with a new to Wisconsin solar installation company, Iconic Energy. They're not new in Illinois, but they're new here. And I am just learning. My background is not in electrical anything. So I'm just here to lurk and learn.
That's great. Well, happy to have you.
Thank you.
Okay, Jess Bannicky, if I got that name right. Are you able to unmute?
Oh, no, Mike.
Sorry, no, Mike. Got it. Thank you for those who are responding on the chat. Appreciate it. Let's see, Jason Heindel.
Sure, Jason Heindel. I'm an electrical engineer working for a company called AZO. I'm in Milwaukee. We are an Australian-based company, but provide and design control systems, SCADA systems for renewable energy, microgrids, utility scale, solar, battery storage systems. The whole renewable energy enchilada.
Okay, very good. Thank you. Appreciate you joining. Let's see, the names kind of move around. I saw, Jeff Stone. Oh, there you go.
Jeff Stone, I'm a consultant with Kapur Consulting Engineers in Milwaukee. We have offices around the eastern part of the state. And I'm a former utility regulator at the PSC and a recovering politician. So interested to hear a little bit, continuing to learn more about renewable energy. And I work on a lot of regional infrastructure issues.
Mm-hmm. All right, thank you very much. Let's see, we'll try to get through this side. Josh Stolzenberg, welcome, Josh. I know you.
Thanks. Yeah, I'm with Northwind Solar in Central Wisconsin. We're a solar design and build company.
Of course. Okay. Thanks very much. Ben Nelson.
Good afternoon. I'm with Emmons and Olivia Resources. We are water resources engineering consultants and have done all kinds of work supporting utility energy delivery projects for Madison Gas and Electric, American Transmission Company, and Alliant Energy, and are more recently supporting solar development projects through resource inventory, planning with local government units, and civil and environmental design.
Okay, very good. Welcome, Don Peterson. I see you have no mic. And right, okay. And then see, Todd, can you actually, I didn't give you a full chance to give yourself a little intro, but.
Oh, sure. Yeah, I'm Todd Montevideo. I'm new to Madison Gas and Electric. I've been with Madison Gas and Electric for a couple of years now, and I'm a manager, renewable engineering and distributed energy resources. Been in the energy industry for about 30 years, and participated. I guess my background is in distribution substations and more recently renewable engineering. So I have a variety of different areas that I've covered, not super deep in all those areas, but I guess for people that are doing renewable interconnections, I've been involved in that for quite some time, both as on the substation and distribution side as well as the actual projects now. So if we have discussions on that, I can contribute in those areas.
All right, great, thanks.
I'm anxious to learn from all the people on here too. There's a lot of people with interesting backgrounds. This should be fun. Yeah.
Great, thank you, Todd. Got a few more. Mingxing Zhang, if I got that right.
Yes. Hi, Lauren. Hi, you all. I'm Mingxing Zhang, a second-year graduate student at University of UW-Madison. And I'm also in the energy policy and analysis program. I'm really interested in electrical engineering, even though that's not my background. I'm studying policy and public affairs, but I'm interested in how solar energy and also other renewable energy can affect the low-income communities, and how can we utilize those renewable energy to deploy, to use them in all the different situations. So that's why I'm here to learn and to, I'm very happy to learn more about the distributive integrate.
All right, thank you. Glad you're here. Eric.
Hey, good afternoon. Eric Kostecki with WPPI Energy, program manager for our renewable energy grants for nonprofits for our member utilities. WPPI Energy is a wholesale power provider for half the municipals in the state of Wisconsin, and then 7 in the UP and 3 down in Iowa. And I'm also the chair of WIDERC, which I think that name has popped up a few times over the course of the days here, and we have our meeting going on tomorrow. But also, WIDERC's can be heavily involved with the interconnection rules updates. So really just kind of tuning in, try to get some ideas. And Todd, I expect might see more of each other here going forward. So
yeah.
Thanks.
Great, thanks, Eric, appreciate it. Just a couple more. Ingrid Nam, if you care to say hello.
Yep, my name is Ingrid Nam. I'm with Appleton Solar. We're a solar electric installation company near the Appleton area, so the Fox Cities by Lake Winnebago, and just here to learn a little bit more about the industry.
Great, welcome. Jason Bacon.
Afternoon, I'm Jason Bacon. I'm a sales and business development with Premise. Premise is an EPC out of the Twin Cities, and we're just here to learn a little bit more about Wisconsin.
Okay, very good, thank you. John Hanson.
Yeah, I don't have a camera, but I'm a retired health professional. Concerned citizen, just here to learn a little bit more.
Okay. And then I see Mike Nicolosi, and then I think we'll jump in because that's sort of the end. Mike, if you're able to say hi.
Sorry, guys, took me a minute to unmute. Mike Nicolosi, founder, owner of Rethink Electric. We're primarily in the Chicagoland area in the ComEd territory, and interested in learning about Wisconsin and what the market has to offer.
Okay. All right. Well, Thanks, everybody. I appreciate everyone being willing to step up to the microphone and say hello. As I mentioned at the outset, this was conceived as an opportunity to kind of discuss some electrical engineering issues that come up on distributed generation projects in the solar field, as well as really any form of distributed generation. My experience in DG is primarily on the solar side, with a little bit of battery storage coming up in the very recent past. And then certainly we anticipate a lot more of that happening in the future. As I am an electrical engineer, I had imagined this would be, kind of trying to be a technical conversation. And it's great that we have a big range of backgrounds of people on the call, some more on the technical side and definitely in the utility world, and then other people with kind of scientific backgrounds of all stripes that kind of want to learn more about the specifics of distributed interconnection. I did not create a presentation per se, but I did kind of tailor it, hoping to get people who are active in the industry to be able to weigh in on some of these topics. And so I'm going to just go along those lines here and share my screen and see if we can get a conversation going. And that way, we'll like I said, we'll try to get a fruitful discussion going if people are still willing to kind of weigh in on topics. So if you see my screen, I believe you do.
Yes.
Todd, you can be,
Yeah,
yes.
I can see it.
Right. So here's my top screen. So this is a list of topics, and they're pretty clearly engineering topics that come up on distributed generation. These are relevant to solar projects, although they are not solar specific. We can certainly talk about them in the context of a solar project, but they're not in any particular order here. It was a little bit stream of consciousness for me, and if we find that some are not of any particular interest, or if people would like to weigh in, then we can move on. So but I will try to address these topics and set them up maybe with the eye to the audience having kind of a broad background. And so I'll try to set some context when it may be helpful. So all these projects, the whole context for this discussion for me is going to be about, sort of taking a typical solar project perhaps and using that as the context. So given that, I'm going to see if I'm going to share my screen on a specific type of project diagram that might be helpful for people to see. Let's see, sorry, let me find my, this is it. So, okay. And are you still able to see the single line, or are you able to see the single line diagram that I'm presenting now, or is it still showing the?
Nope, we've got it.
Okay.
Got it. It's good.
Okay. All right. Sounds good. So I'm showing, this. Apologize for those of you who don't typically look at engineering drawings like this, but I'll kind of give you a quick walk through the anatomy of a solar project. And as we represent it from the standpoint of the interconnection, and then that'll be the springboard for further discussion. So up here, we're calling out the distribution system. We're talking about distributed generation. So we're talking about an energy generating facility that ties into utility distribution system, it's probably a voltage anywhere from 34 kilovolt down to even possibly as low as 4 kilovolt. And that depends what region we're in and what state and all in the history of the utility industry in that area. But, you know, very commonly it could be 12 kV, 24 kV. And just to kind of quickly walk through what you're seeing here so you can understand conceptually, we have the main power connection of whatever the voltage is. So this would be an overhead conductor, possibly on wooden poles coming up to the fence of a solar facility. And then you're going to have what might be called a recloser, which is essentially a circuit breaker, which the utility would often put in that would provide protection to isolate their system from the plant if there's ever any kind of fault within the plant. Then you come to some metering equipment and eventually a disconnect that provides a sort of a permanent and, well, I shouldn't say permanent, but a long-term and visible disconnection of the utility system from the solar plant in the event that maintenance needs to be done inside the facility, or the utility has determined that the plant should not be interconnected to the utility. Then you have additional equipment, possibly another meter owned by the owner of the plant as a means of recording how much power is generated. And then you have another type of circuit breaker device, again, a recloser. So this is what I would call a smart type device. You could use a fuse, or you could use a recloser that has microprocessor controlled relays, such as various different types of products on the market. But this would be kind of the more Cadillac approach for protecting a plant, and one that is more likely to be employed on a larger plant. The plant I'm showing here, the diagram, this is a plant that's about 20 megawatts. And so if you have a sense of the scale of that, we talk in the Midwest a lot of projects that kind of fall into a community solar garden type definition of being in the 1 megawatt range. And what you have here is an indication of many different step-up transformers that transform the voltage, the low voltage AC that is produced by the individual inverters at the project from the solar PV, and then the power is generated and transformed up to 34 kV through a system of underground cables and transformers. And the transformers are daisy chained one to another through the underground cabling. So this is at the highest level how the plant is kind of put together. You can see here from the diagram, each of these transformers is connected to an inverter. The inverter is what converts the solar PV, the energy from the solar PV to AC, so it can be then injected into the grid. So didn't mean to go too far into it, but I just wanted to give a sense of the context for the additional things that I was going to dive into. So I guess I'll do a little brief pause there. Simply, if there are any questions anyone would want to ask about this before we go into kind of the individual subject matters associated with a plant like this.
I'll just want to mention one more thing, Drew. It's probably some people, this might be understood by a lot of people, but maybe not everybody. This, when Drew mentioned this is on a distribution system, typically most distribution systems are radial. So there's one path to this site. There's not typically multiple paths, although utilities do have some networked systems. There are some places where we have networked distribution. And in addition, to add maybe a little bit more complexity, distribution automation, a lot of utilities are starting to install distribution automation, which will allow you to automatically, connect reconnect portions of the system in the event that you have a fault to try to restore power to as many people as possible. But there's one path to this site, so that's it's important for certain parts of the discussion.
Right. And so when the distribution utility is assessing a specific interconnection, they're going to be looking at their system as a radial. If it's a radial system, it may still have a sort of an emergency connection to as part of a loop system that could be, you could close the switch and serve the system from another source. And so you probably have to evaluate both of those when you're looking at incorporating new distributed generation.
Yeah, typically the utility will, they'll evaluate the primary source, and then as you try to look at alternative ways to connect that in, like if you need a backup, that's additional studies, and it can become more complex, I guess, is probably the most important part. But, yep.
Any comments, questions on this from the folks on the line? Okay. I will proceed then kind of with that context and to talk about the various subjects. So here's a list of electrical engineering topics. These are maybe, potentially a little bit obscure to those that don't have the specific electrical engineering background. We'll just kind of wade through them and see where we get some points where people may wish to discuss. Just by way of background, installation coordination, I give a little summary here, is just, the selection of equipment, specifically lightning arresters. So these are arresters which are employed throughout the utility system and then employed on the customer generation as well, in order to protect the equipment from voltage surges within the limits of the installation of the specified equipment. And so we typically do this type of work. The utilities do this type of work with reference to IEEE standards, notably this specific standard C6222, which is the guide for application of this type of surge arrestor or lightning arrestor, kind of terms used interchangeably. And then, when you select this type of equipment, you are going to be selecting arresters, and you often, when you're moving forward with an interconnection, you're getting involved in a discussion with the utility about what's called grounding effectiveness. Grounding effectiveness will relate very closely to some of the considerations for selecting your lightning arresters. Again, the lightning arrestor is there to prevent surges. Surges can be caused most commonly by lightning, either direct strokes on utility lines or nearby equipment, but also just switching operations, connection of some energy storage through capacitor banks, essentially. That can be another source of switching surges. So as a practicing engineer on these projects, I find that there is some work to do with the utility when moving forward with the projects. Some, what we call installation coordination is coordinating essentially within the equipment of the plant, but there is coordination that needs to be done with the utility also, because the utilities selection of their installation levels and their arresters can have impact on how the whole system performs together. A surge that may start on a utility overhead line may travel underground through cabling and could potentially represent a threat to a transformer that's owned by the plant. And therefore the utility equipment that is used to the surge arresters that exist on the utility line play some role in reducing that. So we find that we are, when we are doing an engineering effort to bring up, develop plans for construction, we find that we do rely on that utility information in terms of understanding what their system is. Although sometimes not all utilities are completely forthcoming about how they design their system. They may not be. They may not wish to have their design choices sort of be reflected in how the plant is designing things internally. That's something maybe, I don't know, I could ask you about, Todd. Is that what's your experience? You don't have to be specific to your employer, but just your experience in the field,
Sure.
How that it might be coordinated.
Sure. I mean, I think definitely you want these devices to be coordinated within the plant itself. And then we don't talk about the studies that are performed by other groups. So you'll be performing a study typically for the plant itself. In parallel with that, the utilities performing studies for larger facilities that are being put on the distribution system, and they're looking at installation coordination. They're looking at and in particular, you mentioned things like the faults due to lightning or faults on the distribution system. Those can create voltage transients. People call them surges. But then also a common way to get a problem is after the substation opens up the recloser in an attempt to de-energize a distribution feeder, say after a lightning strike or some type of an accident where you need to de-energize the system to make it safe. These generation facilities will still generate for a short period of time until their protection systems take over. And during that time frame, there's the potential under certain configurations that you can over voltage the insulation on devices like back to the substation and even back to the transmission operator. So the transmission owner and operator, they do similar types of studies to make sure that those short transients that can occur while we're waiting for the system to recover from a fault, that those don't damage equipment because there's the potential you could have a short duration surge that the arresters can address. But then again, as you're aware, you can have a long duration surge, which actually cause permanent damage. And now you're not just impacting even just potentially that one site, but potentially other customers on the feeder. So those studies are important, and sometimes they end up changing the types of devices or cause engineering changes that need to be done to make sure that we don't cause a problem for the rest of the customers on the system. And it is an example, the projects that we've done more recently, the Mauryfield Solar, Dane County Solar, Mauryfield in particular, we had to consider that and change some of the configuration of the equipment. And in that case, it was to change the transformer configuration, which I know is something that we have on our list too to potentially talk about.
Right. Yeah.
That's my experience with it. Both as a distribution, putting distribution on the system or distributed energy resources on the system, as well as being the substation distribution side of it as well. So,
how does the arrestor dissipate the energy?
The arrestor dissipates the energy by conducting current directly to ground. You can see, can you see my cursor?
Yes.
Okay, so that's a terminal where a ground wire would be connected, and the arrestor is technically, the material is called a metal oxide. It says resistor or varistor. The material inside is extremely, its impedance is extremely sensitive to voltage. So it essentially conducts no current at all up to a certain voltage, one that is the characteristic of the arrestor is selected such that surges of a certain magnitude, therefore a certain voltage magnitude, will sort of all at once, to oversimplify, conduct all of the current of the surge through the arrestor to ground. Now, it's not quite as simplified as that, but the essence is that it's a very good conductor once there's a very large voltage over it, but it conducts almost nothing at all other times. And so, yeah, you had the chemical engineering background, is that
Yes.
right? Yes. Okay. So yeah, it's a metal oxide, zinc oxide typically, I believe, and yeah, that's a whole science. But it there's, during a surge, there could be 10,000, 20,000 amps being conducted straight through that.
So yeah, like over time, it's the energy is being dissipated as heat, and over time the temperature is rising in that. So sort of it's a countdown as to whether you can clear that surge quick enough, and if you don't, you can permanently damage that surge arrestor, where they can even fail violently.
And you can think of this as a pressure relief valve, essentially, like on a water heater.
Sure. Great, thank you. Appreciate it.
Yeah, so I had a couple other questions. I think we can move on maybe to the next topic. But in the event that there were some other electrical engineers on the call, trying to get a sense of how has selection of arrestors for the utility or for other engineers been evolving as we get more experience with distributed generation? Are we getting into more detailed calculations? And it sounds, essentially we are to some degree from what Todd's saying. And I don't know if there are specific instances of known failures that are connected with any of this. In my experience, there have been issues where arrestors did fail when there wasn't proper note taken of the voltage rise on the distributed circuits, on the distribution circuits when generation was added. So I was seeing things like that more back in 2010 when we first started seeing big waves of solar being implemented on the East Coast. And each year since I kind of define 2010 as a real threshold year where we're starting to see a lot of bulk solar going in and starting to see 1-2 megawatt plants going in on the East Coast. The experience with this has been just, a phenomenal ramp up on the part of utilities and consultants. So, I think that over time, therefore, some of the studies that we need to be done are being done more carefully and more proactively than in the past. I'm going to switch to the next topic. And this is another very detailed topic, protective device coordination. Effectively, it relates to how the plant and the utility, what devices are in place to de-energize circuits when faults occur either in equipment or in cabling, in order to reduce the amount of energy that is released, either a cable that could fail, a transformer that could fail. It's a very detailed field, and any distributed generation project is going to have multiple overcurrent devices which are there to protect equipment, and therefore, again, there needs to be tight coordination between what the plant is doing to protect itself versus what the utility is doing. And there are ranges of equipment that can be used that are and ranges in cost, using fuses, which are essentially like the old time fuses you might have had in your home electrical panel, to going to more sophisticated devices that are essentially computer controlled and looking for characteristic signs of faults. And at the smaller project size, the 1 and 2 megawatts, employing a recloser or a breaker is considered something that, it's a cost that is, I think, in my opinion, warranted due to the increasing functionality we get out of those devices, and the increasing sophistication that is needed in protecting the plants. But there still are a lot of plants that are just fuse protected. And I don't know, Todd, if you could weigh in if what you're
Sure.
seeing.
Yeah, you know, our projects are like you described. They're larger projects, 5 megawatts and up. So on those projects, we do detailed protection studies, and we do that with customers as well. If a customer or IPP were to come on our system, we would do a similar type of a study that we would do for ourselves, where we evaluate the protection all the way from the substation to the final device, with the idea being we want to make sure that we don't we don't cause reliability problems for other customers, and at the same time we don't want to take the plant off unnecessarily. So when these studies can result in changes to the distribution system and reconfiguration of the distribution system to make sure that that we don't create, like I said, problems for the other customers on the feeder. And what that could mean is maybe changing the devices that are on the distribution feeder. Anytime you buy it closer to a substation, it makes it a little simpler. And as you get further out on the feeders away from the substation, and you have more of these types of devices in between there, it can add to the complexity. So this is definitely something that on an individual project has to be considered, but then also as a role of trying to figure out how we can put more DER on our distribution system. This is an area that we need to think about on how we build our feeders in the future, and how we configure our feeders in the future so that they're more accommodating for this type of energy. Obviously, these weren't conceived of 40 years ago when these systems were first started designed. So it's something that can be a challenge at times, especially like I said, if you're quite a ways away from a substation out on a distribution feeder, that can make it more complex. Mm-hmm. Yeah, these studies are done by, we will do these studies, MG&E will do these studies, and then the American Transmission Company in our particular area, they'll do these studies as well for certain size plants. So once you get to a certain size, you can even impact their systems, or we can impact their systems, I should say. So they'll perform studies as well.
Mm-hmm. And you mentioned kind of making the grid more I guess suitable in the long term for bringing on this type of energy, and that there's a lot of discussion about smart grid all the time. I think it becomes pretty fashionable it has been for a long time, for people to say, hey, the grid is outdated and it's 1900s technology in a 21st century world. And I guess I always pause a little bit thinking, mm-hmm. Well, it's done, it's a job, and now the what's demanded of it is changing. And so to have the opportunity to inject generation from in two directions, either actual generation or storage, and it just means that the engineering problem has changed and it needs new solutions, and a lot of those solutions exist. It just in a lot of cases there's a cost in order to create that new superhighway essentially.
Yeah.
Okay, I'm ready to move forward. Any other thoughts on this topic? Maybe at some point, Eric Kostecki, I'll ping you if you see anything that you'd like to comment on, if you're still there, that kind of relates to the WIDERC stuff. And because I'll admit I have not been directly involved, and I've been intending to get more involved. And let's see, I tried to check the chat.
I don't see anything out there yet.
On the chat? Okay. I got a notification there was there was a new chat, but since I'm sharing my screen, I'm having a hard time seeing it.
No.
Hold on a second.
I don't see any other comments yet.
Okay, I see. Yeah. I see Stephen Ferns is he was wondering about PDF copies. We can certainly make a PDF copy of this discussion available, by the way, of the presentation. So I guess moving forward here, I'm going to get back to sharing my screen. See, time check, it's 2:46, so we got about 15 minutes left. Time flies. Sorry. Okay, moving forward. Grounding studies. So again, to those who are not quite familiar, one of the topics that comes up on a solar plant and in any electrical facility, honestly, is the idea that when there's a ground fault, meaning some normally non-current conducting components of the plant, say for example a fence or an equipment enclosure, if they are to become energized, possibly because of, say, a cable has now touched the interior of an enclosure, that sort of thing, you can have a situation where while that remains energized, there is a chance that somebody touching the fence and standing on the ground would be subject to what's called a touch potential. And so that's something that electrical engineers take very seriously. Traditionally in electrical substations, IEEE standard 80 provides detailed methods for evaluating the degree of that hazard based on all the engineering inputs, the amount of available fault current, the duration of that will last, because all these protection systems we're talking about are employed in order to respond as quickly as possible to this type of occurrence. And it's not uncommon for the whole system to be shut down, or the specifically faulted system to be shut down in somewhere from 3 to 5 cycles, which in our electrical system means 3 to 5 60ths of a second. So the faults are interrupted very quickly, but even with that, it's necessary to evaluate whether that type of occurrence is enough to cause harm to humans if they happen to be touching one of these things. So it's something that's of importance for both evaluating the hazards within the plant that would be, for exposure to personnel working for the plant owner or utility, or, even the general public if they were to be outside the plant and happen to be touching the fence. So we perform these types of grounding studies on plants. The inside the plant in a solar array, it's not uncommon to have to look in detail at what we call the touch potential around the solar arrays themselves. Again, in the event that somebody is touching the array at the very moment when these faults occur. And I mean, we should keep in mind that these faults are exceedingly rare, but that just goes to show kind of the degree of care and due diligence that the engineering looks at these very unlikely events in order to demonstrate that the plant is still safe.
They're rare, but they're important for that one time that they do happen, that people can feel comfortable that when they're at the site that they're protected.
Yeah, if it happens to occur while a group is touring the plant or something, it has been engineered so even for that rare occurrence it is safe. So this slide just kind of raises some questions, again kind of directed at an electrical engineering audience, which we mostly do not exactly have here, but kind of talking about raising questions about the specific methods to evaluate this. And what I can just say what we are seeing that, more and more we are conducting full detailed studies on these projects, even on the smaller size project down to 1 or 2 megawatts. And and I'm talking about ground mounted projects. I perhaps didn't specify that to begin with. When we're talking about a 1 to 2 megawatt project, though it's possible to get, do rooftop projects of that size, when you get into 1 and 2 and above, we're typically talking about ground mounted projects. And, we're starting to see in Wisconsin, many of those going in the smaller range, and then in the hundreds of megawatts now for the first time we're beginning to see. I guess, Todd, maybe going back to you, are there specific requirements that MG&E gets into with respect to whether a study like this is done, or are you more focused on just satisfaction of National Electrical Code, which doesn't necessarily mandate a study such as this being done?
Yeah, on our own projects, we would definitely want a study to be formed. And MG&E is a smaller company, so we rely very heavily on our consultants to do these types of studies for us. So when we're doing a solar project, we rely on Westwood or some other company that we're working with to perform those studies. Back when you get to our own systems, standards typically are not for the generation portion of it, but your typical distribution system standards are usually the way that we address this. So someone creates a standard that evaluates what we would expect to see within our facility, and that's what we design to. But our solar facilities, certainly we do have grounding studies done on those, and we do not rely on strictly like NFPA, or I should say NFPA, but we don't rely on like those standards for our generation, for when we build a generation site. We evaluate them one by one.
Right.
Or the consultants, like people like you, do that for us.
Correct. All right, I'll move on. Another safety related topic, and now we're at 2:53, I'm noting, so I'll kind of go through and make sure, just take one last chance to open up for any remaining questions. But arc flash is another topic. Arc flash is, if you're not familiar, it's referring to essentially the thermal energy that's released during an arcing fault, where electrical energy is essentially passing, where current is passing through air and creating a plasma that generates a great deal of heat. Personnel in the vicinity of that are going to be exposed to that what we call the arc flash incident energy on the surface of their skin and their clothing. And so we perform typically studies that assess what the fault levels are, and therefore how much energy can be released when under the assumption of somebody working on live equipment at an assumed distance. And the studies are based on IEEE and NFPA standards that dictate what sort of assumptions are reasonable for the different voltages and classes of equipment. The result is an incident energy calculation that will determine what sort of protective equipment, PPE, how much, I guess, essentially thermal energy, the clothing and the full mask and shield and gloves can need to be able to withstand for somebody to work on live equipment. So this is something we're producing on pretty much every project, and again, it's an item of coordination with the utility. Todd, like to weigh in here?
Yeah, no, I think that probably one of the most important things is really tight coordination with the utility. You might, I've noticed on some of the projects I've worked on in the past, not necessarily at MJ&E, but and actually primarily projects that were over in the Minnesota, Iowa area, that if you don't really work tightly with the local utility, that overly conservative assumptions can result in some incident energy levels that would be really, really high. And as a result, what can happen is you can end up with some situations where the PPE required to work on equipment is pretty intrusive and makes it difficult for the people to work on the equipment. And I've seen that in the past, in particular on some of the wind projects out in the, like I said, the Iowa, Minnesota area, where the incident energy levels were so high that it required the facilities to be taken offline to do any type of maintenance. So this is an area where I think it really pays to do a lot of detailed engineering and make sure that you get the right information into the study before you have the study performed. I guess that's my main suggestion, is really pay attention to this one so that you don't end up being overly conservative and end up really hindering the operations people that have to work on the facility.
Right. Yeah, it's a very important one from a safety standpoint, and it's been, I mean, arc flash, the attention paid to this in the utility and electric power world over the past, say, 20 years has been a pretty transformative thing. It wasn't regarded, it wasn't recognized and treated as rigorously as it is now for years and years, although it resulted in, it was certainly a safety threat. So it's been a kind of a revolution in that way, and now all equipment is labeled essentially with with enough information so people can understand how to work on that equipment safely. Hey, it's 2:58 and we got about 2 minutes left. I didn't get through a lot of what I had put in as sort of topics, but then again, I think that this was meant to just sort of maybe whet the appetite a little bit for people who had a curiosity about this. And you can see the other topics I had. I'm happy to make this a little presentation, the outline I have here, available probably through Renew, if that can be done, Lauren.
Yep, if you send it, we'll post it on our website by tomorrow, and everyone can come download it when they have time.
Okay, great, thank you. And I mean, I've been kind of holding the floor mostly. I guess with a couple minutes left, is there anyone who has a question about or just a desire to mention a specific thing in relation to these engineering topics? Okay. Let's see, I guess there was one more question that was in the chat. If we don't cover some of the topics, could you give us links to suitable discussions? Yeah, I'd be happy to provide, I can be contacted separately. I'll make sure my email address is in the presentation. And so, I'm certainly open to people reaching out and for interests on these topics. Like to, anything I can do to have people be more informed is, great from my standpoint. So with that, I guess, I think that kind of rounds off our talk. Apologize we couldn't get through all the things I had thought of, but hopefully it was interesting for folks. Definitely please reach out to me if you, once the presentation's made available. And thank you, Todd, for joining. Thanks to everybody. Thank you very much to Renew, Lauren. And I just, thanks for the opportunity. So everyone have a great day.
Thank you both for your presentation, and thanks for everyone who came today. We'll see you next year.
Yes.
Thank you. Thank you. Bye.
Bye-bye.